Hello, everyone. I hope you're having a good Wednesday. Welcome to the Chem Help ASAP live stream. I think we have fixed the sound issues. I'm going to check in with OG Benchmarks and make sure that he can hear me okay. It looks like my mic is working just fine. Hopefully there's no static. Okay, great. Audio is good. All right. Sorry about last week. I am not sure what happened, but I am glad that we've gotten it fixed so that we can finally talk about quantum numbers and electron configurations. So we're going to do really a very quick and basic look at quantum numbers because you can get really deep into this. But don't worry, we're not going to derive particle in a box at this point. We're just going to talk about what the quantum numbers are and what they refer to physically, and then we'll jump right into electron configurations. All right, and as always, please feel free to post questions in the comment section, and I will answer those as we go. All right, let's go ahead and get started. All right, so first, we're going to talk about the four quantum numbers. Now, each electron has its own unique set of quantum numbers, which is why we need four. And the different quantum numbers will refer to different physical properties of the orbitals that the electrons are in, except for the last one, which talks about the electron itself. But let's just start with our principal quantum number, n. Now, this number, it runs from 0, 1, 2, 3 on up, and it is going to give the size and the energy of the orbital. So, as you would expect, the larger the value of n, the larger the orbital and the higher in energy the orbital. So our lowest and smallest energy orbital is going to have an n equal to 0. Okay, so that is our principal quantum number. Next, we have L, which I'm not, there we go, now I'm working. L, which is our angular momentum quantum number. Now this is tied to n. So our values of L are going to run from 0 to the value of n minus 1. So it depends on what n is to then figure out what your values of L are. Now, our angular momentum quantum number is going to determine the shape of the orbital. So I'll show you pictures of the orbitals. Some orbitals, at least to me, kind of look like flowers. Others are spheres. Others kind of look like dumbbells, but we will see those pictures. But that is what L is going to tell us. It's going to tell us the shape of the orbital. Our next quantum number is m sub L. Now, it is also tied to L and therefore n. So your values of m sub L are going to run from negative L to L. So you can see how these all tie together. Generally, you determine n first, and then that determines your value for L or values for L, and then that determines your values for m sub L. Now, physically, m sub L, or the magnetic quantum number, is going to give our orientation and space of that orbital. So again, when we see the pictures of the orbitals, this will make more sense in terms of how these orbitals are oriented in 3D space. Our final quantum number deals more with the electron itself. So remember how I said each electron has a unique set of quantum numbers. This last quantum number makes sure that when you define four quantum numbers for an electron, it refers to only one electron. And that is the quantum number m sub s, which is the spin quantum number. Now, electrons, as we'll see in the orbitals, you can have a spin up orientation and you can have a spin down orientation. And we usually signify that with either a plus 1/2 or a negative 1/2 value. So those are our four quantum numbers. And again, they're all linked to our electrons and our orbitals. And the main reason why we dive so deep into electrons specifically is because we really want to know how atoms, how elements are going to react, how they are going to bond, how maybe bonds are going to break, how bonds are going to form, or how are they going to reform, how are they going to rearrange. So we are very, very interested in the electrons and their behavior. Hence, all of these special numbers just for the electron. All right, so we're going to keep these numbers in mind. And what we're going to do next is we're going to define. All right, so if n equals 0, what does L equal? What does M sub L equal? Or, well, our values for M sub S are always going to be plus half and negative 1/2. And what does that mean in terms of orbitals? Okay, so here on our next slide, we just have this big table. Now, this is not an exhaustive table of all the quantum numbers, obviously, but this is going to give you a really good idea of how these quantum numbers are tied together. So let's start with a value of n equals 1. So if you remember, our values of L go from 0 to n minus 1. Well, if n equals 1, 1 minus 1 is 0. So there's only one value for L, and that value is 0. So when n equals 1, L equals 0. Now we're going to go to M sub L. And if you remember, M sub L runs from negative L to positive L. Well, when L is 0, we don't say negative 0 or positive 0. M sub L is also one value. It is simply 0. Now, what does this mean in terms of the orbital? It means there is one orbital, there is one orientation. This orbital is actually the 1s orbital. And you can see here, you have one orbital, and the number of electrons that can be held in that orbital is 2. Again, this ties in with the M sub S. So you're going to have a spin up and a spin down in that one singular orbital. I'm not going to do this for all of them, but let's take a look when the value of n equals 4, because then we're going to get multiple values going. So when n equals 4, what does L equal? Remember, L has a range. It's going to run from 0 to whatever n minus 1 is. Well, n minus 1, in the case of n equals 4, is 3. So L is going to run from 0 to 3. So we have 4 different values for L. This is totally normal, totally fine. Okay, for each of those values of L, we are going to determine what M sub L equals. So we've already done this for L equals 0. That is 0. We saw that up in this first row right here. So when L equals 1, M sub L is going to run from negative 1 to 1, which means you have negative 1, 0, and 1. When L equals 2, this is going to run from negative 2 to positive 2. So we're going to have 5 values here. And you can see the same thing is true when L equals 3. We're going to have 7 values right here. Okay, so what does this mean in terms of what orbital we're talking about? Well, again, we've already seen when L equals 0 and M sub L equals 0, that's the s orbital. Now remember, this is the 4s orbital because our n value is 4. So it is a larger orbital. It is a higher energy orbital than our 1s. When L equals 1 and M sub L equals negative 1, 0, 1, these are called our p orbitals. Again, they're 4p because n equals 4. And there are 3 of these orbitals because we have 3 different values for M sub L. When L equals 2, these are the d orbitals, and there are 5 of them. And when L equals 3, again, we have 7 values. These are called the f orbitals. You can see there's 7 there. And then for the number of electrons, remember, each orbital can hold 2 electrons. So for the f, where there are 7 different orbitals, we can hold a total number of electrons of 14. All right, so now hopefully you can see the correlation between n, L, and M sub L. Of course, M sub S is always plus 1/2 and negative 1/2 because, again, we have the spin up and the spin down, and that is always going to be true. All right, now that we have kind of just, again, a table of quantum numbers, not an exhaustive table, but a general table of quantum numbers, let's see the pictures of the electrons, or not the electrons, of the orbitals themselves. And I think this orientation, this value of M sub L, is going to make a little more sense. So if I go to my next slide, here are all of the different orbitals that exist in the atom. So our first orbital that we're going to talk about is the s orbital, and we saw that with our table over here. So when n equals 1, L equals 0, M sub L equals 0, and that is our 1s orbital. So remember, with M sub L, when you have M sub L equals 0, there's only one orientation. And that is because it is a sphere. So if you think about holding a ball, you can rotate it in space however you want, and the orientation looks exactly the same. Like you couldn't, assuming it's not a ball that has any markings on it, if you were to look at it, close your eyes, and I were to rotate it 90 degrees and you were to open, the only way you could tell is if you saw my hands were different, but you can't tell from just the ball itself. So there's only one orientation in space for the s orbital. So the next orbitals I want to look at are the p orbitals right here. So this is when, I'll go back to my table, this is when L equals 1. So you can see these are actually the 2 p's, but we saw them down here with the 4 p's. And there are 3 values of m sub L, which means there are 3 different orientations in space for these p orbitals. So if you look at this picture here for p sub x, can you see how the orbital is oriented along this x-axis? Now, if I were to take this p orbital and rotate it in space, you could absolutely tell that it had been rotated. You wouldn't need to look at my hands at all. That would be p sub z, and you can see it's oriented along that z-axis. So the same is true for p sub y. It's going to be along the y-axis. So these are the 3 orientations of the p orbital. And again, this ties into the 3 values of m sub L. So hopefully you're kind of starting to make a connection between the quantum numbers and how many values there are and what the orbitals are looking like and their orientation in space. Okay, so let's talk about the D's and the F's. And these are ones that I think they kind of look like flowers. So here are the D orbitals. And you can see there are 5 of them. So let's go back to our table. When we have our d orbitals, it means that L equals 2, which means the values of m sub L run from -2 to +2. So we have 5 values. We have 5 orientations in space. And you can see how that is true. We've got 5 different shapes here. Now, a lot of these are oriented not so much along an axis, but along a plane. So let's take a look at, well, not that first one. Let's take a look at dxz, and you can see how the lobes have that orientation along that xz plane. So the same is true for like dyz is along the yz plane and dxy is along the xy plane. Now you can see we've got some other ones here. So we've got 2 other orientations. This is dx squared minus y squared. And you can see, again, it's got a different orientation than these ones that are along planes. And then we have a final one, which I think looks kind of cool. That is dz squared. But again, we have 5 different orientations for the d orbitals. So that's why it can hold 10 different electrons, because we've got 5 different orbitals. They're all d orbitals, but again, their orientation in space is different. So finally, so hold on, I've got a question from Giselle. Those d and f orbitals are so hard to draw. Yes, I will draw the s orbitals and I can generally draw the p's, but the d's and the f's, if I try to draw those by hand, it's pretty much a disaster, which is why I always go to these professional drawings. But the F's, I think, really tend to look like flowers to me. They've got a lot of lobes. We have one that kind of looks like the dz squared. This is fz cubed. Sorry, that z cubed is really, really tiny. But again, you can see how they all have different orientations in space. There are 7 of them, because let's go back to our table. So if we have an L of 3, that means our values of m sub L are running from -3 all the way to 3, which means we have 7 values, which means we have 7 f orbitals, and they all have a different orientation in space. And this is, again, why we get 14 electrons in there. And it's these guys in green down here. I would really not attempt to draw these by hand, because that would be completely confusing. Hence why I got a very pretty picture to show you tonight. Okay, so let's move on. Now we've got our quantum numbers. We know what orbitals they work with. So how else do we use these? Well, what we want to know is, where are the electrons? And this is going to tie into where the electrons are. So what I've got on the left-hand side is called an energy orbital diagram. It gives, again, the relative energies of the orbitals. So you can see I've started here with the 1s. Remember, that's n equals 1. That is our lowest energy orbital. The 1s is just the sphere. There's only one orientation. And then I have the 2s. And so you can see I have all, well, not all of the s's because that diagram would be massive, but I go up to 6s in this diagram. Now, a kind of interesting thing happens when we have orbitals with different orientations, because when they're just oriented in space differently, it doesn't change their energies. They still have the same energy level. So if we look at the 2p orbitals, you can see I have 3 different slots for these. These are, again, for the 2px, the 2py, and the 2pz. And sometimes on these energy diagrams, you will see these labeled as such. I didn't bother to do that because it really doesn't matter in terms of putting electrons in. You just know you have 3p orbitals. And you can see here are my 5d orbitals. I didn't go all the way to f's because my diagram just got way too big, but you can imagine if you have the 4 f's, you're going to have 5 slots. They're all going to be the same energy. So when you have these orbitals, like the p's, the d's, and the f's, and they just have a different orientation in space, and they have the same energy, they are called degenerate orbitals. So let's actually write that in. Maybe I'll write it in black. So these are degenerate. Let's put it up here. These are degenerate orbitals. And it doesn't mean they're bad. It just means they have the same energy. I always thought it meant that they were, somehow inferior. All right. So now that we have our energy orbital diagram and we've got our orbitals in the right order, okay, where do the electrons go? Well, there are 3 rules that we follow when putting electrons into this energy diagram. And these are the 3 rules you can see right here. So the first rule is the Aufbau principle. And you can see I simplify this. Start from the bottom. The Aufbau principle is you start with your lowest energy orbital, and that is always going to be the 1s orbital. So if you have 1 electron, you can't just randomly decide to plop it into the 4s or one of these 4ds. No, it's always going to go into the lowest energy orbital that it possibly can. When we talk about excited states and ground states, then you can get some other things going on, but we are all in ground state here. We are going to fill from the bottom, from the lowest energy orbital, and move our way up. You can think of this like filling an apartment building. You're going to fill apartment 1A first, and then you're going to fill apartment 1B, or you're going to go to the next level. So you're not going to start filling from, say, the 4th level. You want to fill the 1st level first, and then you're going to go to the 2nd level. It's the same with electrons. Okay, so that is our first rule. Our second rule is the Pauli exclusion principle. So remember how I said each orbital can hold 2 electrons. This is your m sub s, but they have to be a spin up and a spin down state. So each orbital, each of my little slots here, can hold 2 electrons, but I have to specify that they're spin up and spin down because remember, they have a unique set of 4 quantum numbers. And our last rule deals with our degenerate orbitals. This is Hund's rule right here. So in Hund's rule, it states that wherever possible, put electrons in their own orbital. So you keep them unpaired until you have to pair them. So this is, again, if you think back to kind of the apartment building complex, if you could have an apartment by yourself, that would be great. That would be your first choice, right? But your landlord, let's say, isn't going to add new apartments or go to the next level until all of the apartments are filled. So when we're filling like the 2p, we're going to put 1 electron in each of these first before we add a second electron in. Now, don't worry, we are actually going to do examples of this, but I just want to be clear about what the rules are. Now let's see. Okay, it doesn't look like there are any questions so far, but let's start putting electrons in and seeing how this all works. Okay, so let's just start with our easiest. Let's start with hydrogen. So our hydrogen atom, and pardon the small size of this periodic table, when we do more electron configurations, I will go to a larger one. I should have maybe said this at the start of the stream. If you have access to a periodic table like right in front of you, I do recommend using one that's right in front of you so that the one here on the screen can just be a quick reference. So let's start with the hydrogen atom. How many electrons are in the hydrogen atom? Well, if you remember how to count protons, well, and neutrons, but really protons and electrons, we're dealing with a neutral atom here. Hydrogen has an atomic number of 1, which means it has 1 electron. Okay, so hydrogen has just 1 electron. It's a very small atom. Where does that electron go? Well, again, we have to follow our rules. So our Aufbau principle says that we need to start with the lowest energy orbital level, which is going to be the 1s. So I am going to put that electron there in the 1s orbital, and that is where it is for hydrogen. And there's only one, so like that's all I write on my energy diagram there. The Pauli exclusion principle doesn't yet apply to us because I only have 1 electron in this orbital. And of course, Hund's rule, not dealing with degenerate orbitals. Okay, so that is hydrogen. Let's clear our diagram and let's do some more. Okay, let's go to one that's got more electrons. Let's go and let's do some P's. So let's take a look at oxygen here. So how many electrons in oxygen? Well, it has an atomic number of 8, which means 8 protons. So if we're dealing with the neutral atom, which we are, it means we have 8 electrons. Okay, I'm just going to write this down right here. This is my note. I have 8 electrons, and I have to show which orbitals these 8 electrons are in. So again, starting with Aufbau principle, I'm going to start with my lowest energy orbital, or start from the bottom as I wrote here. And I can put 2 electrons in. Now, this is where Pauli exclusion principle comes in. If I'm putting 2 electrons in, you notice I have 1 up arrow and 1 down arrow. Now, we kind of, you can see we kind of shorten this. We don't actually show the full arrow, but you absolutely can. You put it in however you want. Just make sure you show 1 is spin up and 1 is spin down. That's the Pauli exclusion principle. Okay, so I've taken care of 2 electrons, right? So where does the third one go? Well, again, I'm going to fill that apartment building from the bottom on up, which means my next orbital with the next highest energy is my 2s. Again, I'm not going to jump to the 4d orbital. I'm going to start from the bottom and I'm going to fill up very systematically. Okay, so my next orbital is the 2s. It can also hold 2 electrons. So I'm going to go spin up and spin down. And now I have 4 electrons that I have put into my energy diagram. So I have 4 more electrons to deal with. Okay, so now I need my next highest energy orbital, which is going to be my 2p. This is where we're going to bring Hund's rule into effect. So again, I have added 4 electrons here. I have 4 more to go. So first, I put 1 in each of my degenerate p orbitals. So I have added 3 electrons there. I still have 1 more electron to do because I have only added 7 so far. So where does that 7th electron go? Do I put it in the 3s? Not yet, because our 2p's are not completely full. So our last electron is going to be paired up in one of the p orbitals. So you can see you can think of this as a maximum number of unpaired electrons, or you can think of this as a maximum number of apartments that only have 1 person is what we want to do. So that is Hund's rule. This is the energy orbital diagram for oxygen. So let's go ahead. Let's make sure there are no questions first. All right, let's go ahead and do another example. So we'll do some more electrons, but you can already start to see that the orbital energy diagram is really helpful, but it's kind of large and it's going to get cumbersome really quick. So we wouldn't do this. But what if I had to go down here and do like berkelium with 97 electrons? I'm just not going to, I could do that in an energy diagram, but I don't want to do that in an energy diagram. But first I want to make sure we're really comfortable with the smaller atoms in the energy diagram before we move on to electron configurations that are written a little more simply and more shortly. Okay, so let's see. Let's go on to, let's do magnesium. All right, so magnesium, atomic number 12, we have a neutral atom, so we have 12 electrons to deal with. Again, I'm following Aufbau. I'm going to do Pauli exclusion, and I'm going to do Hund's rule. I'm going to show you how I'm going to start with a 1s, and I'm just going to fill all the way up. All right, so 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is the energy diagram for magnesium with 12 electrons. So it's really, once you kind of get the hang of it, it is actually pretty easy, but you've got to get the hang of Hund's rule too, and getting used to putting 2 electrons in, spin up and spin down. But once you do a couple of these, hopefully it gets really simple and you start getting faster and faster. Okay, if there are no more other questions, we are going to start doing electron configurations without the energy diagram. We are just going to be basically reading off the periodic table. So when you read off the periodic table, there are really 2 main ways to do this. And I have a strong preference for one, but I will talk through both of these. So you might recognize, let me switch to this. You might recognize this diagram here. This is a diagram to show you what order the energy of the orbitals goes in. So it's really trying to get you to do this diagram, but just kind of written out instead of putting it in a big sheet, just writing it out. So what you do is you follow this roadmap and you go 1s, and then 2s, and then 2p and 3s. Oops, sorry, I missed. And then 3p and 4s. This is not the way that makes a lot of sense to me. You can see I just made a mistake right there. So what I found when I was a student, I would almost invariably either write this table down wrong or I would follow the roadmap wrong. And the frustrating thing for me was once that was done incorrectly, then all of my electron configurations were wrong. And they generally all had the same error because I had made the same error at some place. Like maybe this 2p I had put up here. I think I did that once, or I had skipped some things. So that is a totally valid way to do that. And there are many students who use this roadmap and use it perfectly, and it is not a problem. So I don't want to say that is not a valid way to do it, but make sure you're using a method that makes the most sense to you. So this method just really didn't make a lot of sense to me. I like to just use the periodic table itself. So I'll show you what I mean. And let's do a color here. So if I am thinking about the s orbitals, then the s orbitals are actually found in these 2 columns right here. These are the s orbitals. So like I have the hydrogen atom, and you remember it just had 1 electron in the 1s. Well, it's in the first row. It's in my, what I call my s block. So it's the 1s orbital. And if you remember when we did magnesium, we also finished. We filled up the s orbital. So you can see magnesium here still in the s block, but it is in the 3s block. So again, you're going to see how I'm going to organize the periodic table just into blocks so I know where I am in terms of what orbitals. Okay, so that is the s block. Then we have these 10 columns here. This is the d block. These are the d orbitals. So anytime you move through the d block or you end in the d block, you're going to have an atom that has some electrons in the d orbital. We have these 6 columns right here. These are the p block. Again, if you think about when we did oxygen, we ended in the P's, we ended in the 2 P's, and oxygen is in the P block in the second row. And then way down here, these kind of lonely guys right here, these are the F block. So this is how kind of I organize electron configurations in my head. I use the periodic table to show me where the different electrons are. Now, the other cool thing about the periodic table, and I've kind of been mentioning this, is if you have these numbers written, and these are kind of small here, to the far left, then that gives you, well, that gives you the energy level, that gives you the size, and that, so for hydrogen, there's a 1 here. This is the first row or the first period. That is the 1s. If I'm talking about rubidium down here, which is in the 5th row, that is the 5s. So it's really cool how your s's and your p's are going to correlate exactly with whatever row or whatever period you are in. So let's do a couple of these with the blocks here, and I am going to, I should have done the laser pointer for that. I'm just going to try to erase it a little bit so it's not quite so crowded. All right, so let's talk about how we are going to write these electron configurations, and we're going to start with hydrogen again. We'll start with our simplest one, because remember, hydrogen only has 1 electron. Now, we've already done this. I mean, I erased it, but you remember it was just in the 1s orbital. So again, if I'm looking at the periodic table, I'm going hydrogen. It's in the first row. It has 1 electron, so that is going to be 1. It is in the s block. That is s. Again, there's only 1 electron, and so you write that superscripted. So when you're writing these, the format is really important. Your numbers written in front of the letter for your orbital are going to be what we call inline numbers. So they are going to be right in line, just like you would write any kind of normal number. Then you are going to put what orbital is in. This is S, P, D, or F. And then the number up here that is superscripted, I think I said subscripted last time. Anyway, it's superscripted. That tells you how many electrons are in that orbital. So in the case of hydrogen, there's only 1 electron, and it is in the 1s orbital. So you want to be careful, especially as you're first learning these, to remember what numbers are in line and what numbers have the superscript, because otherwise you're going to have everything jumbled up, and I'll show you how that can go awry if you don't keep your formatting done properly. So let's go ahead and go on to oxygen, just like we did before. Now, when using the periodic table, just like you would use the table up here, I always think about, I'm going to start in hydrogen's place. But again, you can, if you're using the roadmap, you're going to start in the 1s orbital. So I have the 1s orbital right here. And again, this is kind of how I think of it. I count spaces where the atoms are, because remember, as I go from hydrogen to helium, my atomic number goes from 1 to 2, which means my number of electrons goes from 1 to 2. And I just count spaces, just moving through the periodic table, starting in the first row, then going to the second row, et cetera, until I hit the element that I am trying to do the electron configuration for. So I have hydrogen and helium. They're both in the first row. And so I'm going to fill that 1s orbital up. So that is going to have 2 electrons. Now there's something that's kind of cool, which you've probably noticed. You go, wait. Helium is over here in the p block, but you didn't write a p orbital down. Well, depending on what periodic table you're looking at. In this one, yes, absolutely. Sometimes you will see helium written over here for this very reason. And sometimes you'll see hydrogen written over here. So that's why, again, periodic tables definitely have variation. But remember, we're in that 1s orbital, and you can even think back to your energy diagram here. We've got to fill that 1s orbital first before we move on to the 2s orbital. Now, the main reason why helium is put over here is it is a noble gas, and so in its reactivity, it's going to follow the noble gases, so it is put in that column. All right, but back to oxygen, because that is what we're trying to do here. So oxygen, I have now taken care of 2 electrons, but oxygen has 8. All right, so I've made it all the way across to helium. Where do I go? Well, I've finished the first row. I just go to the second row. And again, if you're following your roadmap here, you can see you go 1s, and then you're going to come to the 2s. So now I have the 2s orbital. Again, I'm in the second row. My value of n has increased by 1. So my 2s orbital, and again, I'm looking at my s block. How many elements are there? 1, 2. So I have 2 electrons in my 2s orbital. Then I have this big space here. And you can see in that space, I've left the S block and I'm moving on to the P block. So I am now no longer in an S orbital. I've jumped to a P orbital. Well, which P orbital have I jumped to? Because there are a lot of P orbitals. Well, I am in the second row. So this is my 2p orbital. Again, if you're using your roadmap, you can see you go 1s, then you do 2s, and then you do 2p. So again, you can see both of these methods totally work. It just depends on what makes the most sense to you. So I'm in the P block and oxygen is right here. So I know I'm not going to fill up the P block. So I'm not going to get all the way to the end of this period. So how many electrons then do I have in this P orbital? Well, I've already taken care of the electrons here. I've got 4 already. So I have 1, 2, 3, 4 more electrons, and that is 2p4. Now, when you're writing electrons this way, you'll notice that Hund's rule is kind of moot at this point. You could write out 2px, 2py, 2pz, but that's not generally how we do this. We just say, hey, in the p orbitals, we have 4 electrons, and it is assumed at this point that you know and understand Hund's rule, and you can know that only 2 of those are paired and 2 of those are unpaired. Again, we're following our energy diagram here. We've gone 1s, 2s, and then 2p. All right, so let's see if there are any. Okay, make sure there are no questions. The first time you do this, I know it feels like, what is going on? So let's do a couple more, and then I'm going to switch over actually to the bigger periodic table, but I want to keep this table up here just a little bit longer, just in case you're using it and following it, and you can see how it does follow exactly with what is supposed to happen here. So let's do one with a few more electrons. Let's maybe go ahead and do chlorine here with 17. So chlorine has 17 electrons total. And I know that because its atomic number is 17, and especially right now, we're just dealing with neutral atoms. So where do I start? I always start up here with hydrogen. That is in the first row. It is the s orbital. How many electrons? 1, 2. All right, that's the first row taken care of. I've now got to go to the second row. So I'm going to the second row right here with lithium. And so that is back in the S block. So this is 2s. How many electrons? 1, 2. I'm still moving across. I'm going across this big gap here from beryllium all the way to boron. But now I've switched from the 2s to the 2p. Okay, so let's count across. How many electrons? 1, 2, 3, 4, 5, 6. And then I'm done with the p block. I've got no more. And again, you can see 2p, it should have 6 electrons, because if you remember, p has 3 degenerate orbitals. So again, all of this ties together and it should all be consistent within each other. Okay, so I'm not at chlorine yet. This is actually the electron configuration for neon so far. So I'm not done yet, but I am done with the second row. So now I'm going to go to the third row. So now I'm in the third row. I am back in the S block. How many electrons? 1, 2. And then I'm done with my S block. I have to go across my big gap here, go across to aluminum, but now I'm in my 3p's. How many electrons? I just need to count all the way over to chlorine. So that's 1, 2, 3, 4, 5. And that is the electron configuration for chlorine. Now, the cool thing that you can do just to check to make sure that your electron configuration makes sense is, remember how we said that there were 17 electrons in chlorine? So let me switch colors here. If you add up your electrons, remember your superscripts tell you how many electrons. This should add to be 17. So let's see, this is 4 plus 6 is 10, is 17 electrons. So if you're doing electron configurations and you're not quite sure, that is a really quick and easy check just to make sure you have the correct number of electrons, that you haven't skipped a row or you haven't skipped a block. You ought to get the number of electrons that is expected for that atom. Okay, so doesn't look like there are any questions. Let's go on to our larger periodic table. So I am not going to have this table up in the corner. I'm just going to have a large version of the periodic table because I want to talk about the D's and the F's. So again, if you like to use this table, just make sure you have it next to you so that you can reference it. Okay, so here is my big periodic table, and let's make sure I don't, okay, good. I wanted to make sure that my video did not cut anything off there, but we can see helium. Okay, so again, let's just mark out all of our blocks. And this is something that I would do certainly for homeworks, but so this is the S block, but sometimes your teacher might allow you to bring in an annotated periodic table, and that would be something that I would do if I was allowed to bring in an annotated periodic table where I could write my own notes. Okay, these are the D's. That's really messy. D, okay. Again, these 6 columns here, and this time, nah. I thought maybe I wouldn't include helium, but it is part of this block. These are your P's, and then down here are your F's. Okay, and again, that's just why I like this periodic table. It's got really big numbers here on the left, so I can keep track of what row I am in, which I really like. Okay, so we've done a couple of elements. Let's do calcium next, so it's going to be right before we hit that D block, just so we review everything first, and then we'll go on to scandium, which has got that first electron in the D block. So calcium. I am starting with the electron and hydrogen. That is in the first row. It is in the S block, and again, remember that you can think of helium as being over here also in the S block. So that is 2 electrons in the 1s. That's my first row taken care of. I'm going to the second row, back to the S, and I have 1, 2 spaces there going across, still staying in the second row. Now I go to my 2 P's. I'm just counting across 1, 2, 3, 4, 5, 6. That's it for my 2 P's. Now I'm going into my third row. So that's 3. Again, I'm back in my S block. How many? 1, 2. And then I'm switching blocks. Again, I'm going across, and I'm in the P block. This is a 3P. How many electrons? Let's count it up. 1, 2, 3, 4, 5, 6. Great. That's it for my third row. I'm not to calcium yet. I have to go to my fourth row. I'm back in the S block. How many electrons? 1, 2, and that puts me right at calcium. Again, I should have 20 electrons, so let's count up. I have 2, 2, 6, 2, 6, 2, and that should be 20, so that's 10, and that's it. So we have 20 electrons. Again, it's always nice to double check and make sure you have the correct number of electrons. All right, so once we go from calcium and we pop over to scandium, it means we've added 1 electron. But you can see I've got a line here. I've switched from my S block to now my D block. Now, the thing to remember about D's is when you're using the periodic table like this, not when you're using this table, this will already set you up for that. That's an advantage of memorizing this table here. When you go to the D's, you're going to go back 1 from whatever row you're in. So I'm going to put this rule down here. D's go back 1. So this D electron here for scandium is in the 4th row, but it is the 3D orbital, if that makes sense. So instead of it being the 4D orbital, we go back 1. It is the 3D orbital. Just to go back to our table here, you can see we've got 4s, and then it's going to pop you to 3D here, which is exactly what we're doing. Again, just make sure you get that table written down correctly if you're using it for a test or a quiz or something like that. Okay, so D's go back 1. So let's go ahead and do the electron configuration for scandium. Now, this, again, it's going to follow calcium exactly until we get to the D's. So that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Again, that is calcium right there. And then D's go back 1. So this is 3D. How many electrons? Well, there's just 1 space there for scandium. So that is 3d1. Again, if you were to add all of this up, you're going to get 21 electrons. We already counted up these as calcium. That's 20. So you now have 21 electrons. So that is what is special about the Ds. A similar rule applies for the Fs. So Ds go back 1, Fs are going to go back 2. Fs go back 2. But I don't want to do F electron configurations quite yet, because you can see at this point for scandium, our electron configurations are getting long. And if we're going to deal with these guys down here, again, if we're going to do like cerium with 58 electrons, then our electron configuration is going to go really, really long. So we want a simpler way to write this. So if there's one thing that chemists like, is they like to simplify things as much as possible. Actually, I'm going to erase these electron configurations so that we've got space for the others. So we are going to use what is called the noble gas shortcut. And I think the best way to illustrate this is with 2 different electron configurations. So let's get the electron configuration for neon up, and then we'll do the electron configuration for sodium, and I will show you how the noble gas shortcut works. So for neon, again, this is a pretty easy one. We're starting with the 1s. Again, there are 1, 2 electrons there. Go to the 2s, 1, 2. Come across to the 2p, and I have 1, 2, 3, 4, 5, 6. And that is the electron configuration for neon. Pretty simple, right? Now let's do sodium. Still, that is 1s2, and this is the 2s, 1, 2. The 2p, 1, 2, 3, 4, 5, 6. And then finally, we have 3s1. Now, the reason I chose these is because what I want to show you is that the configuration for neon is embedded within the configuration for sodium. So this is what I mean when I said the noble gas shortcut. So the shortcut way that we are going to write sodium, we are going to write sodium as, so again for sodium, we're going to put neon in brackets. And then we're simply going to put what's left outside of the brackets, the 3s1. So when using the noble gas shortcut, the first thing to remember is you have to use a noble gas. So you can't just pick any element you want. It must be one of these on the far right-hand side. Also, you want to make sure that you choose the closest noble gas that is not ahead of the element. So if I'm doing the electron configuration for chlorine, it's really tempting to use argon as my noble gas, but argon has more electrons than chlorine. So its electron configuration is not going to be embedded like we see with neon here within chlorine. So if you're doing chlorine, you've got to choose the closest noble gas, but it cannot have more electrons. So it would also be neon there. So for example, let's just go ahead and write this down. And I'm going to erase my D there. Maybe I'll put it over here. Okay, for chlorine, I can use neon. That's fine. That gives me neon right here. So my next orbital is my 3s orbital. How many electrons? 1, 2. Come all the way across to my 3p, and I got to get to chlorine. 1, 2, 3, 4, 5. So again, we didn't have enough electrons to use argon. We had to use neon. So that can get a little tricky. Just remember, I think of it as it has to be behind the element, but you can also think of it, it has to have fewer electrons than whatever element you're trying to do. Okay, so now we can go and practice some more D's and throw some F's in, and I'm going to use the noble gas shortcut just so I can fit the electron configuration on the page. Otherwise, I don't know if I could fit it on the page. I'd have to write like teeny, teeny, tiny. Okay, so let's do the last configuration before our Fs and then our F, kind of like we did with calcium and scandium down here, where we went just up to the D block and then we went over. So I'm going to do the electron configuration for lanthanum right here. Now, again, this is where different periodic tables do different things. Sometimes this lanthanum is put up here, and sometimes it's put down here with the F block. So you'll see it both ways. But lanthanum is going to be your last element that does not have an F orbital. So I think, I'm going to put this in red. I think of just a really big red line right there. So I can do lanthanum, but then once I hit cerium, I am going to have to deal with the Fs. All right, so let's do lanthanum first. So lanthanum, of course, if you look at the main periodic table, it belongs right here. We need a noble gas. That's the closest noble gas, but does not have more electrons than lanthanum. So I'm going to work backwards, and that's going to be xenon. So that is the noble gas I'm going to use. So basically, instead of always starting with hydrogen, for this time, I'm going to start with xenon. So then I go down to row 6. I'm in the S blocks. So that is 6s, and I have 1, 2 electrons. Lanthanum, I know, again, for this periodic table, it's written down lower, but it really should, maybe you could argue that it should be written up here. This is now in the D block, but remember, Ds go back 1. So it's not the 6 Ds, it is the 5 Ds, and there's 1 electron, so it is 5D1. Now let's do cerium, which is our first element that's going to have an F electron. So cerium, we're still going to use xenon as our noble gas because it is the closest that does not have more electrons. Again, we're going to our 6s, 1, 2. Then we're going to our 5D. Remember, lanthanum, even though it's written down here like it's in the F block, it actually belongs in the D block. So that is 5D1 because there's only one of them. And now for cerium, we've moved into the F block. So remember how I said Ds go back 1 and Fs go back 2. So we're working in the 6th row here. So instead of it being the 6 Fs, we're going to go back 2. It is the 4 Fs. So it is 4F. And then how many electrons? Well, for cerium, I've just got 1 electron in there. So that is the electron configuration for cerium. Now I know this, for especially the first time through, this feels really, really weird, but we're going to practice a couple of these. And we're like, those are the only exceptions that we've got in terms of things that go back. Now it's just practice, 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 practice. So let's do another one. Again, I'm going to erase, so I've got space. Let's do another one in the F block itself. And then I'll show you like these guys down here, I think really are the most difficult. But let's not go to the most difficult quite yet. So let's do something interesting here. Let's do californium. Okay, so californium has 98 electrons, so you could imagine trying to do californium in your energy diagram, massive energy diagram, or even writing out starting your electron configuration starting from hydrogen, which you can do. You can imagine this would be really, really long, which is why we always do noble gas shortcut. Okay, so californium right here, let's find our closest noble gas that is not ahead, so it's got to have fewer electrons. So californium's got 98 electrons. What row is it in? Well, remember, it goes back to this actinium, which is right here. That's row 7. So it looks like radon is going to be our closest noble gas. It does not have more electrons. And yes, I mean, radon only has 86 electrons, so this is going to work. So we're going to start with radon. Okay, so after radon, we're in the 7th row. We're in the 7 S's. How many electrons? 1, 2. Then we go to actinium. Again, on this periodic table, they write it with the F's, but it really belongs with the D's. So this is in the D block right here. D's go back 1. So it's not the 7 D's. It is the 6 D's. How many electrons? Well, there's just 1, and then we switch blocks. Now, once we cross, again, my red line that I drew, we are in the F block, but it's not the 7F block. It is the 5F block. Now we just need to count up electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. and that is the electron configuration for californium. Now, the one thing I'm going to point out is when I'm doing these electron configurations, I am only following the rules. There are exceptions, and especially when you get into these F electrons, some funky things start happening and electrons start changing places. But for right now, and especially when you're first starting out doing electron configurations, you really just want to get really comfortable with the rules and practice with just the rules. And then once you're comfortable with that, go back and learn the exceptions. And you can see why, like some electrons, if they can go half filled, they'll go half filled because they're more stable that way. But for now and for this live stream, we are only following the rules and we are not going to deal with any exceptions. All right, so that's californium. Now let's do one of the difficult ones. So what I have found for students is the difficult ones lie in kind of the lower D and P block here. So let's do the electron configuration. No, let's maybe not do, let's do osmium. I started circling it, we might as well go with it. So osmium. And I'll show you the mistake that most students make when they're doing these electron configurations. Again, noble gas shortcut, let's find the closest noble gas that doesn't have too many electrons, and that is going to be xenon right here. Okay, that's great. Xenon is here. My next row is 6, and that is the 6s, and I have 1, 2. And you go, oh, great, I go to the D block. Okay, D's go back 1, that's 5. If I count across, I have 1, 2, 3, 4. Or sorry, that would be 5. 5D. 5, but we have a problem. This is not the correct electron configuration. So remember how I said you can add up your electrons and it should add to the correct number of electrons? Well, if I start with 54 electrons for xenon here and I add 7, do I get 76? No, I'm missing quite a few electrons, right? Okay, so hopefully you have spotted the error. And this is where this kind of periodic table does help. So I have skipped over this blank spot. Why did I skip over that blank? What's going on with that? I just skipped over it. You can't skip over it. So remember we've got lanthanum down here. It's element number 57. And then we've got hafnium here, which is 72. So again, depending on how your periodic table is written, if you have lanthanum written right here, then the temptation is going to be very, very strong for you to just count straight across to osmium because you're going to forget that you've got to deal with your Fs. So I've put my red mark here, but I'm also going to put a red mark here. So anytime you cross that line, you need to realize that you need to take care of the Fs because, again, lanthanum has an atomic number of 57, but if you go straight to hafnium, you've skipped 14 electrons. That has an atomic number of 72. So let's go back and let's do osmium correctly. So 6s2 is totally fine. Then we go to lanthanum, which again should be in the D block. D's go back 1, so that is 5D1. Then we switch to the F block. So these are our 4 Fs, because Fs go back 2, and let's just count up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Which makes sense. Remember your Fs, you've got 7 orientations. It should hold 14 electrons, which means if you ever forget how many electrons each type of orbital can hold, you can just count it up on the periodic table. It's right there. Okay, so that takes us to lutetium. That's number 71. Now we can go to hafnium. So what have we done? We've left the F block. We've gone back to the D block. We've gone back to the 5 Ds. Now we can count from hafnium to osmium. So here is our 1, 2, 3, 4, 5. Okay, so a couple things I want to point out about this. You have 5 Ds here and 5 Ds here. This is perfectly acceptable. This is a valid electron configuration. However, your teacher may say, no, I don't want you to write it that way. I want you to combine your 5 Ds. Okay, no problem. I would say until you're comfortable, start with your 5 Ds separate so you don't forget those 4 Fs, and then just rewrite with the Ds together. So this would be 6s2, 5d6, 4f14. Again, just follow whatever guidelines or rules your teacher gives you, but know that this electron configuration is a valid electron configuration. All right, let's do just one more of these more difficult ones where, again, you're very likely to skip your F's, and let's see how it works. So let's do the electron configuration, not of osmium. Let me erase this one. Lead, that's one that's always very popular and people recognize. So let's do the electron configuration for lead. It's got 82 electrons, so it has a lot of electrons to keep track of. So let me just make some space here. All right, so lead. Definitely using our noble gas shortcut here. So let's find our noble gas that's appropriate. So that's going to be xenon. It's nice and close, but it doesn't have too many electrons. All right, so once we do xenon, I'm coming across here to my 6 S's, and I have 1, 2 electrons. Then I go to lanthanum, which is in my D's. D's count back 1, so that is 5D, and I only have 1 before I have to skip to my F block. So there's my lanthanum. Now I'm in my F block. These are my 4 F's. Let's count across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which again makes sense because I should have 14 electrons. Now I'm at atomic number 71. I can go to atomic number 72. I am back in the, I'm back in the D block. I'm in the 5D block again. Let's count across. Again, I'm going all the way to lead. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Now be careful. We've crossed a line here. We've gone from the D block to the P block. So I need to stop here at mercury just for a second because that is 5D9. And now these 2 elements are in the P block. So remember your P's, your S's and P's are going to follow the your number that's out here to the left. So I'm now in the 6P and 1, 2. And that is my electron configuration for lead. So these are kind of the 2 most common things, either forgetting the F block because you're just counting across with the D's and you've forgotten that you've skipped over the F block. And also this line like right here and even in here as well. Remember, you go from your D block to your P block there, but if you're really focused and you're just counting spaces, it's really easy to just cross over that line and forget that you've gone from your D block to your P block, and then you have something really weird, like you've got 12 electrons in your D orbitals, and remember, they can only hold 10. But before we go, let's go ahead and combine our D's here. So for lead, we've used xenon as our shortcut, and that's 6s2, 5d1, and 9 is 10, 4f14, and 6p2. And that is our electron configuration for lead. So I hope that helps. I hope that clarifies some of the rules, some of the exceptions, and just how to handle things. Again, you can always use this right here. So you can see here are the D's and then here are the F's. And as long as you follow that carefully, it'll take you right through the different order that you need to do. Okay, so as always, you can let me know questions. So the live stream is ending, but if you have questions later on, you can always put it in the comment section. You can always contact me if you have other questions and other requests for a live stream. So if you're still struggling with electron configurations and you want to see more examples, or you're interested in the exceptions and why those happen, we can do that as well. So thank you very much for joining, and I will see you guys next Wednesday. Bye.